So hello everyone, this is lecture 8 for the quantum mechanics. So today we will study about the de Broglie hypothesis. So before going into that, we will first see the questions I have given you. So these are the questions. I hope you managed to solve it. Otherwise, let me give you the solution. So a 45 kilowatt broadcasting antenna emits radio waves at frequency of 97 megahertz. So how many photons are emitted per second? So the energy of one photon will be given by this 97 to 10 power 6 frequency. So you will just h nu will give you energy, and total energy is nothing but 45 to 10 power 3 joule per second. So you will divide this energy to this. That will give you number of photons. You can see here, this is total energy, and energy of one photon will be this. So per second, so this is joule per second. This will cancel out and it will give you number of photons emitted in the 1 second. Okay, so and the second question was, is the quantum nature of the radiation is important in analyzing the radiation emitted by this antenna? So see, this intensity is very large. So when intensity is very large, then there will be large number of photons emitted, means this number of photons will be very large. So when photons are in the range of very small 1, 2 and 3 photons, then they matters, okay, and they have some significance. But when they have very large number, then this number of photons doesn't have any significance. So this quantum nature of radiation will not be important when we analyze the radiation emitted by this antenna. Okay, it can matter when you will see at a very large distance, when this energy will be down and a very low intensity will be there, so you will have some small number of photons there. So only then it will matter. Otherwise this number of photons will not matter when it is from the antenna. Okay, so that was your answer. So second question is this: if the stopping potential of a metal when illuminated with the radiation of lambda given is this, so we need to find the work function of the metal. So this is the minimum wavelength needed. So let's see. So this stopping potential will give you K max, and this lambda will give you h nu. So you have this formula, h nu equal to h nu naught plus EV. So this voltage is given, electron you know the charge. So you will subtract this from this, you will get your work function. So minimum amount of energy. Now that is called the work function. If frequency is asked, so you can calculate the frequency also. So the cutoff wavelength will be given by this formula. Again, you know h nu naught, so you can find this SC by lambda naught. So lambda naught will be SC by W. So that's how you can find, and EV will be your K max. So third question was frequency is given on the metal, and this work function is given, and we need to find the stopping potential. So this work function given, so find the maximum potential kinetic energy K max. So again h nu equal to h nu naught, means h nu equal to W plus K max. So that's how you can find, just a simple. So if you have W, you can find the cutoff frequency, and kinetic energy of the ejected electron will be given by the stopping potential EV naught. Now this fourth question, frequency is given on 4 different metals and their work function are given. So just calculate the h nu for different, okay, which among these metals will exhibit the photoelectric effect. So when this, if h nu will came out to be greater than this, any of this, means for which this work function will be less than this energy, then you will say that element will emit the photoelectrons. And when this is large for someone, then it will not emit the photoelectrons. So just you need to find h nu first, then just compare. For each one of the metals producing photoelectrons, calculate the K max. So you know the work function, so you can calculate the K max. So that will be just h nu minus work function. Now this question was very important. The intensity reaching the surface of the earth from the sun is about 1.36 kilowatt per meter square. So this amount of energy is received by the earth, assuming the sun to be a sphere of radius this. So sun's radius is given, that radiated like a black body. Estimate the temperature at its surface and lambda of its strongest radiation, then total power radiated by the sun. So what is the means how you can find the temperature at the surface? So you will use the Stephen's law here. So what is the Stephen's law? Now see, this is your sun and this is emitting energy, and whatever energy is emitting, so it will going like in this sphere. So it is spreading like this, means whole energy when at this point when there is earth, so this amount of energy emitted by this point will be same in complete sphere, will be distributed in this complete sphere. Okay, so first to find the temperature, this is your Stephen's law. So energy per unit area per second is nothing but sigma T4. This is Stephen's constant, and this is temperature. So this if we multiply this thing with the area of the sun, then we will get the total energy emitted by the sun, because this is the energy per unit area. Then multiply the area of the sun, you will get the complete energy emitted by. So sigma T4 multiply the 4 by r square. This is r is radius of sun, so area of sun is this. So this will give you total intensity produced by the sun. Now this intensity is distributed in this complete sphere. So this distance between sun and earth is this. So 4 pi r square will be the area of this sphere around the sun, which is consisting of earth. So we'll find the energy per unit area, because this is just like a point in the sphere. So energy per unit area will give you this intensity, which is receiving by the earth. So earth is just a point, and this per unit area will give you energy at this. And this is given in question, that what the energy is receiving by earth is S. So S is nothing but this is total energy emitted by sun per unit area will give you energy received by earth, and that is equal to S. So just substitute the value of S here, and Stephen constant for sun is this, sigma this, and you know the value of R. This is small r is this, capital R is this. So you can calculate the T from here. When you get the T, so now you can calculate the lambda. So it was also asked in the question. So first you will calculate the temperature, and lambda for strongest radiation, that will given by the Wien's displacement law. So lambda max will be 2.8 × 10⁻³ divided by T. Now total power radiated by the sun will be this one, only this upper part. This will be your total radiation. So just calculate this one, and it will give you your answer. You know the sigma, you know temperature, and 4 pi r square. Or you can just multiply S with this, means you know what is the intensity at the earth, and just multiply with the 4 pi r square. It will give you the total intensity at sun itself. Okay, because this will remain same, means this will distribute in here also in this sphere. The whole intensity will be equal to whatever emitting by this point. Just it is spread now. It is more spread as compared to center. So at whatever it is at center, it will remain same up to here. So this S multiplied by 4 pi r square will give you the same value as sigma T4 multiplied by 4 pi r square. So you can just directly calculate the value. Okay. So that's it. That's how you can solve this question. So let's move forward for the today's topic, that is de Broglie hypothesis. Now what is de Broglie hypothesis? So he suggested the dual nature of matter. So first we already know from the 1900 Planck's theory, and in the 1905 we have photoelectric effect. So we produced or proved that there is dual nature of radiation first. So there is wave type nature and the particle type nature. So when we consider the wave, we have lambda and k is nothing but wave vector, and lambda is wavelength. So this is your radiation, this is your lambda. And if we consider the particle, then with corresponding to lambda we have what? Energy, and corresponding to wave vector we have momentum. So that's how they are analogy of each other. So lambda for energy, k for p. Now we can write p in terms of k, means if we want to relate them, both of them, then we can write this relation p equal to h cut k. This is constant. Now from here this k will be h squared is nothing but h upon 2 pi, and k is nothing but 2 pi by lambda. So substitute the value, then you will get this relation, lambda equal to h upon p. Now this relation is for the radiation. They relate momentum of the particle with the wavelength. And if you write this p equal to h by lambda, then this relate the momentum with the lambda of the radiation. So normally radiation have the wave nature, but if you calculate for the particle, then you can check its momentum by h by lambda. So that was the thing we already know. We already proved this from the photoelectric effect. Now de Broglie was a PhD student, and he was in the research. So he suggested or proposed in 1924. De Broglie proposed that why only light has a dual nature, means why just this thing is applicable for the light only. Why not matter? Means any matter, electron, proton, neutron can have the dual nature. Means if this wave can have particle, then any particle exists can have wave also. So that was the proposed thing, means that was the basic idea behind this. So why not matter, electron, proton, neutron can have the dual nature. So he suggested that all material particles should also have a dual or wave particle behavior. So any particle exists should also have the wave particle behavior. So he suggested this, but there was no proof yet. So he postulated that the same relation lambda h by p is also applicable for the particle with non-zero rest mass. Means he suggested that same relation what we are getting for the radiation should also applicable for the rest mass and any particle we have which have the rest mass. So this was the proposed idea, means lambda equal to h by p, and this should be a universal relation which is applicable for the radiation and the matter also. So it should be applicable for both radiation and the matter. So for particle, P will be m upon mv, and you will substitute here, you will get their wavelength. So and we call this as de Broglie wavelength. Now if you talk about for matter, so this relation is valid for only matter, lambda equal to h upon mv, because matter is only can have this mass velocity, so this will give you lambda. So just remember this difference. Now let's say we have any particle like electron. Now any wave associated with it will be like this. So this lambda will be this length. So if this is a particle and it has momentum mv, then this wavelength of this particle, this will be wave. So lambda will be h upon p, and it will be lambda equal to 2 pi over k. Okay, and k is related with momentum, so this lambda will be this, and means for wave lambda will be 2 pi by k, and for particle p will be mv. Now these two are related with this relation, lambda equal to h upon p. So that was the suggestion and the proposed idea by the de Broglie. Now this formula means they understand, means they just said that this is true. Okay, means there is not proof, but they assume that this is true. Now you can apply this formula for different cases, means non-relativistic and relativistic cases. So for non-relativistic cases, means the velocity is very small, so lambda equal to h upon p, you will just simply p in place of p you will write mv. So these are important in the for the point of view of exams. So how they can ask question, it will be like this, means they can say that this is non-relativistic case, then you will use this formula h upon mv, and now you can write this momentum in form of energy, because half mv square equal to total energy, and you can write p square by 2m equal to kinetic energy. Then p is nothing but under root 2m kinetic energy, so it will be h upon under root 2m kinetic energy. So in place of momentum you can write this under root 2m kinetic energy. So you can directly calculate lambda if kinetic energy is given. Now if it is relativistic case, then this mass is relativistic mass, so it will be m naught divided by under root 1 minus v square by c square. You know this formula from the special theory of relativity. You must see my lectures on the STR. So now there is one way to write this formula for the relativistic case. There is another way, means this is your formula, just multiply with c here and c here, so you will get sc by pc. Now this relation is also from the special theory of relativity. So total energy of a particle is given by this formula, under root pc square plus m naught c square and whole square, and this total energy is nothing but rest mass energy plus kinetic energy. So you can now relate these terms, means you can find the value of pc from here. So it will be pc equal to under root, this is kinetic energy k, so under root k plus 2m naught c square. So this will be your relation for the relativistic case. So you will just substitute in place of pc this value. So this is your very general formula, means you can apply this formula for the non-relativistic case and relativistic case both, because for non-relativistic case this will collapse to this formula. Okay, this will resolve to this formula again, because velocity will be very small. So but in general you will use this formula when there is not given if it is relativistic or not. So now this is about the questions, means you must know for one electron any voltage is given, then that potential is called the 1 electron volt, means for 1 electron and 1 volt potential, then this potential energy is called the 1 electron volt energy. Okay, and we call this means this is also the kinetic energy of the electron. Now see, you have this formula. Now in place of kinetic energy you can write EV naught, means V is potential. So if potential is given, so in kinetic energy you will use EV, because EV we already proved equal to kinetic energy in the previous lecture. So lambda is nothing but h upon root 2m EV. So this value of 2me and h, if we solve this value, you will get this 150 upon v. So you can just remember this formula, you don't need to solve this again and again. You can directly find the lambda for electron. This is under root 1 upon 150 divided by v, this is potential, and this value will be in the angstrom. Now how you can see that if some particle in relativistic case or not, means how you can determine. If just velocity is given, then there is no particular boundary between the relativity and the non-relativity, means just you can't decide by just seeing the velocity that this is relativistic case or non-relativistic case. So how you can determine? You will check the rest mass energy. If rest mass energy, this is kinetic energy given, is greater than the rest mass energy, then case will be relativistic. And if kinetic energy is less than the rest mass energy of the particle, then case will be non-relativistic. Always remember this. Only this thing can decide if the particle is relativistic case or non-relativistic case. Okay. And you must remember some numbers. These are very important. For electron, m naught c square value is 0.5 mega electron volt. Okay. So this is relativistic case. Lambda is nothing but sc over, this formula came from here, sc over pc is nothing but this, and kinetic energy will be ev plus 2m naught c square for the electron. So you must remember these formulas, they are very important. Means question is asked from these things only. Now I already told you, if velocity is given, you can't decide if this is relativistic case or not. Okay, then you need to check the kinetic energy first and the rest mass energy. So you need to compare them. And if it is not given it is relativistic or not, then always use a relativistic formula. This will give you always right answer. Now you just remember these number, must remember these number for the exam point of view. Means lambda is given by h upon 2mp ev. So this is for the proton. If you decide for proton, then you can simplify this formula in form of, means multiply c here and it will be c, then it will go c square under inside the under root. So sc over under root 2mp c square ev. So you must remember these number mpc square, mec square, mnc square for different neutron, proton, electron. You must remember these numbers. So, and this sc is constant for everyone. So this sc value will be this. Remember this number. And mec square will be 0.5, mpc square like this, and mnc this. So just if this something v is given, then you can just substitute the value and you can find the answer. So this will reduce your calculation and make it fast. So just remember these number, very important. Now see, this is h upon 2 meg, means this is the same case as I told you here. So this kinetic energy is nothing but ev. So this will be sc by c square. So if you need to find for the electron, you will just substitute mc square here from 0.5, and if k is given, just substitute here, and this is electron volt in the electron volt, so you will get the lambda directly. So you will get your answer very fast using the direct values. Otherwise you can always simplify by substituting each and every value inside this formula. So for neutron, lambda is nothing but h upon 2 mne. So this is kinetic energy. So again you can use this direct formula, 0.28 divided by energy, electron volt and angstrom. So this will give you direct answer. And if it is depending on temperature, means now it is about the gas. So how you can find? So h upon 2 mass of neutron multiply, this is nothing but energy. So energy is 3/2 kT now. This is Boltzmann constant this time. Okay, so this is a relation between lambda and temperature. So with temperature you can also find for a gas or the gaseous system this lambda. Okay, for neutron, if neutron in the, means there is gas of neutron, then for a particular neutron you can find this at any temperature wavelength. So just remember these formulas, very important. Now let's see the proof of this dual nature of matter, means they proved the matter wave. How? So matter have the dual nature. This was proposed by the de Broglie in 1924. So it have particles and wave, and the wave is nothing but matter wave called. And radiation was a wave, so it was proved by the interference, diffraction, polarization. There was many things which can prove the wave nature of radiation. And for the particle nature of radiation, there was experiments like photoelectric. We already see that in 1904. Then Compton effect and many experiments. So they proved the particle nature of radiation also. Then in 1927, there was an accidental experiment, okay, where they proved the particle nature of matter also. So how they did that, let me tell you. This was Davison and German experiment. So originally this experiment was not conducting for checking the nature of the particle nature of the means wave nature of the particle or not. This was originally conducted to check the surface morphology of metal. So there was any metal and they just need to check the surface, if it is rough or what, and what kind of structure it have on the surface. So the experiment was conducted to check the surface. So they can't use the visible light because this wavelength is very large, and the distance between the surface of metal at the surface of metal is less than 100 nanometer. Now to check this, they must take the wavelength which is comparable to this, means less than or comparable to this. Now they can't use this, so they will use they use the small particles like electrons, because for the proton the radius is nothing but 10 to the minus 15 meter approximately. So electron is more smaller than this, so they use the electrons to fire upon this and to check the surface morphology. Okay, so they use the electrons, these are the point particles, to study the roughness of the surface. Now see what was the design of their apparatus. So this was a vacuum tube, and there was the electron gun, and there was your nickel metal and kind of polycrystalline structure of nickel. Now there was some leakage in the vacuum tube, and somehow the gases came inside, means this was the actual case happened. So gases came inside, then when there is air inside the vacuum, then this metal will get oxidized definitely. So this get oxidized and they were unable to check the surface morphology. So what they did, they just take this out and start heating this, because after heating this oxide layer can be removed. So they take this nickel outside and they start heating it. So with heating, this oxide layer removed, and this process is called the annealing. Okay, so with temperature they just remove this, and in this process what happens, when in starting it was a polycrystalline structure, then after heating it will convert to a single crystalline structure. Okay, now just after when it converted to a single crystalline structure, they immediately put it inside this and they fire the electron gun to check the surface morphology. Then what they see when they observe this reflected waves or the reflected electrons, then they observe in the observer detector, they observe some pattern of intensity, means some strange pattern. So they did not see this first. So that pattern was something like diffraction pattern. So they did not know that it is diffraction pattern. They saw this result, means this was the thing, means now they have metal. So they fall the electron here and they received this, then they notice some pattern, and this pattern have some intensity, somewhere less, somewhere more, and they get the maximum intensity at the 50-degree angle. So this was their curve from this detector. So at the 50 degree they were getting the highest density for this kind of structure. Now they shown this complete thing or the experiment in a conference, and when they come to know that this is a diffraction pattern, and they all were surprised, means now this electron is giving diffraction pattern. So they again now they conducted this experiment very well, and again they were getting this. Okay, so now see, if this electron is giving the diffraction pattern, then it must be behaving like a wave. So they considered that if it is behaving like wave, then this is a single crystalline structure. So it is crystal, then crystal will have your crystal planes. So crystal plane will act as your means they will give you the path difference between the different waves, and that is why they are getting a diffraction pattern. So they must follow the Bragg's law, means this radiation or the wave of electron must follow the Bragg's law. So let's find the lambda from this Bragg's law and then compare with this. So they first find the lambda from here. So how they did that? Now nickel metal is a crystal, so it will act like something like this. So this is crystal planes, and this is your interplanar distance d, small d. So this is your radiation falling or the electron wave falling, and at 50 degree they are getting the maximum intensity. So let's say this is your theta angle and this is your theta, so these are same. So this all three will make 180 degree. From here, if phi is 50, so you can find the theta, that is 65 degree. Now all the diffraction things and the diffraction pattern follow the Bragg's law, and Bragg's law is nothing but n lambda equal to 2d sine theta. So this is n equal to 1. For n equal to 1, we know d already for the nickel crystal, we know d equal to 0.091, and sine theta is taken from here 65 degree, and we find it this lambda. So they say that if whatever is falling over it, means in the form of electron there is wave falling, then that wave must have this wavelength to show this diffraction pattern. Okay, because they must follow the Bragg's law. So Bragg's law gives this wavelength, so only this wavelength can give you the diffraction pattern if this is behaving like wave. Now what de Broglie means, now they use the formula of de Broglie, they find it the wavelength, means this is theoretical formula, lambda equal to h upon b, we know this, and this is nothing but under root 150 over v, and this v is voltage. So they given the 54 volts and they find it, this is wavelength will came in the nanometer. So this result was 0.166 nanometer. So theoretically de Broglie proposed this will be this wavelength 0.166, and experimentally we find it this value 0.165 nanometer. So they are almost same, very minute error. So this experiment proved the wave nature of electrons. Now we are getting the same wavelength, that means whatever is falling over the nickel crystal is wave, and the electrons are falling, so it must be a electron wave. So that's how we proved the matter wave. The question will not be coming from this part, okay, but this is a very good for your understanding, and this kind of thing is asked in the interview, so you must know about this. Now see, in 1936 Davison and Germer got the Nobel Prize for this experiment, and G.B. Thomson also, he did this experiment separately, he also got the Nobel Prize. and he was the son of J.J. Thomson. So they are very popular. The father-son duel means J.J. Thomson discovered the electron as particle, and G.P. Thomson proved the electron as wave. So so this was the very popular duel. That's why that the father invented as particle and son gave the wave. So that was the thing. So that's it for the de Broglie hypothesis and the wave particle nature. So I hope you get the point I am trying to convey here. So if you are still confused somewhere and having some issues, then you can put in the comment section. I will try to resolve. Otherwise, that's it. In the next lecture, we will start the actual quantum mechanics, because now it will start. So thank you everyone. We'll meet you in the next lecture.